in the morning session is Ayushi Verma from the University of Canterbury. We've met Ayushi before. She was one of the founding members of the New Zealand Student Space Association, which is an up and growing organization. It's grown from one branch to two, so it's doubled in size in 1 year. As that exponential growth continues, hopefully we'll have branches of the New Zealand Student Space Association around the country. What Ayushi is going to talk to us about this morning is some of the work that she's doing at the University of Canterbury on galaxy morphology and classification. Thank you.
Thanks. All right. Good morning, everyone. My name is Ayushi Verma, and I'm a second-year undergraduate student at the University of Canterbury studying astronomy and mathematics. During my last semester of university, I took an observational astronomy course where I did a research project on a topic that interests me. Over my summer vacation, I took my project a little bit further and did some extra analysis. Here I am presenting to you my work. There are many galaxies beyond the Milky Way. A fantastic example of the extent of galaxies in a tiny corner of the universe is Hubble's ultra-deep field image, taken by the Hubble Space Telescope. This image contains over 10,000 galaxies of varying colors, luminosities, sizes, and shapes. I was motivated by this image to learn more about the morphology or structure of galaxies and to understand how they're classified. Being a student at the University of Canterbury, I was able to use the telescopes at Mount John Observatory, and in order to get started with my research, I researched what galaxies would be observable at Mount John at that time of the year. Factors like the limiting magnitudes of the telescopes, the moon, and the rise set times of the galaxies had to be taken into account. After my observing proposal was approved, I observed my galaxies using 3 telescopes at Mount John, the 0.61 Optical Craftsman telescope, the 0.6 meter Baller and Chivens telescope, and the 1.8 meter MOA telescope. The next and most important step was to reduce and then analyze the raw CCD images. Since I used multiple filters on each telescope to observe my objects, I reduced the images for each filter for each object. Since raw CCD images need to be calibrated first for excess noise and signals like bias, dark current, saturation, and more by first subtracting the biases and darks and then dividing by the flat fields. I used the software Astronz to do this. Once the images were reduced, I aligned the stacks of multiple exposures for each object, for each filter, by aligning the WCS apertures, or bright stars, you can see right there, in Astronz. I then stacked the images together by an average intensity projection type to get one image for one object for every filter that it was imaged in. I took this a little bit further and did some extra work to stack these multiple filters together and create a colored combined image for many of the galaxies. And I now have an appreciation for astrophotography, and I'm hoping to do some more astrophotography of my own. So now that I had visual CCD images for each galaxy that had been reduced and calibrated, I classified them according to Hubble's tuning fork diagram right here. The tuning fork diagram was devised by Edwin Hubble, who classified them according to shape. On the left, we notice some galaxies with large nuclei and no arms, and these are ellipticals. They generally range on a scale of E0 to about E7, E9, based on their ellipticity. On the top rung, we have galaxies with relatively small nuclei and arms, and these are spiral galaxies. And the ones on the bottom, they're spiral galaxies but with bars, and these are barred spiral galaxies. And they range on a scale of about A to C depending on how tightly wound the arms are. There's also a certain class of galaxies which can't really be classified as elliptical, spiral, or barred spiral, and these are called irregular galaxies. Based on the visual images I had for each galaxy, I classified them as you can see here. Here we have a few barred spirals and here we have a mixture of galaxies, including an elliptical galaxy and an irregular galaxy. That's actually the Cartwheel galaxy. It's one of my favorite galaxies. Here we have another mixture of galaxies, some barred and unbarred spirals, and one I wasn't sure whether it was an elliptical or a spiral, could be possibly lenticular galaxy. So one of the difficulties I faced when using Hubble's method was distinguishing between an elliptical E9 and a spiral S0 galaxy, like that galaxy over there. It was hard to tell what kind of galaxy it is despite examining all the filters and under different scales and conditions using the software. Perhaps using the Circe profile might shed some light on this matter. And so the next step was to use models to fit to the data and verify that my earlier visual classifications were correct using the light mass profiles of the galaxies. And I used something called the Circe profile, which essentially classifies a galaxy according to its light mass profile, which is the distribution of mass as a function of radius of a galaxy, measured by the surface brightness in this case. And the Circe profile is given as this equation over here, where these parameters mean those things. The most important number, I guess, or parameter for our purposes here is n, and it's usually a number between half and 10. It's worth noting that the Circe profile of a spiral galaxy is usually modeled by n equals 1, which makes the Circe profile like that. Notice the lack of the Circe index number n. This shows that spiral galaxies are modeled by an exponential trend. Hence, in the context of Circe profiles, we call spiral galaxies as exponential galaxies. Elliptical galaxies, on the other hand, are usually modeled by n equals 4, which makes the profile equation like that. This shows that elliptical galaxies are modeled by what's called as the Circe index, 1/4, and so they're called as Circe galaxies. In theory, my hypothesis was that the Circe profiles of the galaxies should look something like this, where the black line, the black curve, represents spiral galaxies with an exponential profile, and the red curve represents elliptical galaxies with a Circe profile. Therefore, in order to use the Circe profiles to classify my galaxy data, I had to first extract a surface profile brightness for each galaxy. And I did this using the software DS9 and drew a projection line at 4 different angles, like here, for each filter for each galaxy. This is part of the code that I wrote to analyze the surface brightness profiles. First, I normalized the plot, and then read off the values for R and central pixel from the normalized plot, and entered these as parameters in the function. The value of n I estimated from the earlier visual classifications using Hubble's diagram. So for example, for NGC 720, I earlier estimated that it's an elliptical galaxy, so I used a value of n equals 4. This gave a great fit of the Circe profile, and so I used the value. For the galaxy NGC 1291, I estimated it to be a spiral galaxy, so initially I used the value of n equals 1, but the resulting Circe profile didn't quite fit. So I incremented the value of n in intervals of 0.1. So I went up in n equals 1.1, 1.2 until n equals 1.5 was a good fit for this particular galaxy. So I'll quickly walk you through how exactly I analyzed this data. Here we have NGC 1097, which is a barred spiral galaxy, which I classified it. And so I estimated n equals 1. For each angle that I extracted the surface brightness profiles for, in the green filter of the galaxy, I calculated the uncertainties in the data, indicated by the green bars, and I'm not sure if you can see it, but they're purple dots, which is the actual data. And in the lower graphs here, we have the pink is the actual data, and the purple foreground curve is this fitted Circe profile. Initially, I tried n equals 1, but that didn't give a good fit, so I went up in intervals until I found n equals 1.5 was a good fit. I did the same for the infrared filter and the red filter. And again, I did the same for another galaxy, NGC 1232, which I thought was a spiral galaxy. And I tried n equals 1, but that didn't work, so I tried different n values until n equals 1.2 was a good fit. Same process for the infrared and red. And please just bear with me for half a minute more, but NGC 720 I predicted to be an elliptical galaxy. I repeated the same process. Since it's elliptical, I used n equals 4, gave a good fit, so I just used that. Again, same for the infrared and red. So to save you some time, I've just collated my data into a little table here, where I've listed the galaxy and my predictions for them, and then what n value was found to be a good fit for each of the filters. This set of data was observed in the BNC telescope in the green, infrared, and red filters, and this set of data was observed on the optical craftsman telescope in the blue, green, and infrared filters. So it wasn't always easy to visually distinguish between E9 and S0 lenticular galaxies, and so I used the Sirsic method to try and resolve this, and tried both n equals 1 and n equals 4 to fit to the Sirsic profile to the data. In theory, if it was an elliptical, it would have a better fit with n equals 4, or if it was a spiral, it should have a good fit with n equals 1. Using this seemed to resolve a few of the unclear distinctions between E9 and lenticular galaxies. Another issue was not all my predictions were actually correct. Despite classifying the galaxies first according to Hubble's method, and then using Sirsic profiling, some of my galaxy classifications were still wrong when I checked them against the literature classifications. This means that even by visual inspection, it may actually be hard to figure out the type of galaxy it is due to many factors. Yeah. So remember that the Sirsic profile describes the light mass distribution of mass as a function of radius in the galaxy, and that the Sirsic profiles that I fitted showed either a bell curve-like shape or a spike shape. In the case of the bell curve, it indicates that the mass, and that means light intensity, gradually increases as the center of the galaxy is approached and then decreases. And this shows that the mass is somewhat evenly distributed across the galaxy. And that's a Sirsic exponential profile predicted for spiral galaxies. Or this sharp spike graph shows that a lot of the mass is concentrated in the center, and that's what you would expect for an elliptical galaxy. But this theoretical trend was not noticed in the light curves produced for these galaxies. Some spiral galaxies showed sharp spike-like shapes, which was theoretically not predicted. As you saw in the plots earlier, there doesn't seem to be a correlation or some sort of trend or pattern between the shape of the Sirsic profiles of different types of galaxies. Meaning, for example, looking at the spiral galaxies, some display exponential type profiles and some display actual spiral-like profiles. And also due to limited data, it was hard to make a decisive inference for elliptical galaxies, except for a general remark that usually elliptical galaxies can have reasonable Sirsic fits at n equals 4. Additionally, there seems to be no trend to distinguish between barred and unbarred spirals. One possible reason for no correlation could be the quality of the data. At the time of observing, the weather wasn't that great, and there was a full moon, which would have affected the amount of light collected for the galaxy, which affects the data. The main reason for these inconclusive results are that there are several scientific factors which I had not considered or that I assumed. For one, the orientation of the galaxies was not taken into account. Okay. I'm not quite sure what happened. Right. Okay. So we don't know if the galaxies that I observed are face-on or edge-on to us, and that would affect the surface brightness profiles collected, making it hard to infer a conclusive result. Before I did this extra analysis, I didn't consider using different angles of galaxies and didn't expect the surface profiles in different filters, so my previous results indicated a general distinction between barred and unbarred spirals, as I noticed that in general the spiral galaxies had n equals 1, while barred spirals usually had n equals 1.5. This wasn't always the case though, and this method was incorrect. This is probably a spurious correlation, which is why I discarded my earlier set of data and did my analysis again. Some possible improvements I'm aiming to incorporate in my further research for this topic is to do follow-up observations of a wider range of galaxies, including a lot more elliptical, lenticular, irregular, barred, and unbarred spiral galaxies. So it would be probable to get some sort of trend or conclusion to understand about the morphology of galaxies when we have a bigger sample. Another improvement I'm working on right now is trying to find an average surface brightness profile for many angles of the galaxy. One method I'm trying is to simply plot the average surface brightness profile for each angle, so 0, 45, 90, 120 degrees, like in my previous slides. And then trying to find the average sort of light curve, an average plot. And I'm trying to work out how to fit a surface profile to this set of data, and whether it's even possible. I'm also reading up on a variety of different publications which deal with different methods for classifying galaxies. Sadly, I only stumbled across these not too long ago, which means I couldn't really incorporate it in this slide. But it is an area that I am looking into. And despite the fact that I couldn't find solid results, I have still learned a lot from this project. I was a first-year university when I did this course, and I only had a minimal amount of physical, mathematical, and programming skills necessary. After finishing the course and doing all this extra analysis, I am now a lot more knowledgeable about scientific computational methods, which is analyzing the data, writing code to analyze the data, and understanding the physical meaning behind the results. I also learned a lot about the scientific research process in astronomy, from coming up with ideas for the project, planning how it's going to be done, carrying it out, analyzing the data, and most importantly, presenting it. Speaking of presenting, I did a variety of formats of presentation for this project, which includes writing up reports and giving presentations, making a poster, and it's just given me a lot of new skills and knowledge. I also have an appreciation for astrophotography, and I'm excited to use my newly gained astrophotography skills sometime. I also now know how large-scale professional telescopes like the ones at Mount John work, and I'm hoping to someday work on a project where I can collect data from telescopes like those. Just as a general aside, after this course and project, my passion for astronomy was further solidified and made me realize that I want to pursue this kind of career where I can work with data, think about how it relates to our understanding of the universe, and to communicate this data to my peers and you, the audience. Doing this also enabled me to seek an internship with a professor at Brown University in Rhode Island, the US, where I'm working on a project about the study of dark matter in galaxy clusters. I've also started experimenting with astrophotography and borrowed a friend's camera to get this really cool image of the Milky Way at Lake Tekapo a few months ago. And I was also motivated to spread my love and passion for astronomy by starting up the NCSSA association, like in my presentation yesterday. I was also motivated to start a blog, right here, where I write articles about different topics in astronomy and science which interest me. And finally, thanks to this project and this course, I've seriously started considering a variety of topics in astronomy which inspire me, which I can then pursue as a career. Attending this conference is so useful in my pursuit of knowledge for my passion, and meeting really interesting and knowledgeable people. from whom I learned a lot in the span of 3 days. I would like to thank Dr. Karen Pollard for helping and encouraging me with this project, and to Astronz for providing grants so I can attend this conference for the 3rd year in a row and be able to stand here and talk to you about all my work and my passion. Thank you.
All right, anybody got a couple of quick questions for Ayushi before we go to morning tea? Yep, down at the back, Simon.
Thanks for a great presentation. Does your data show, or does the CERSEC relationship distinguish between the activity of the black hole in the centre of the galaxy or not, and does that have an effect on it?
Yep, so black holes, you said.
Yeah. Does the activity, so the centre of the galaxy is a star-forming galaxy, I would have thought that with
Yep.
the extra or the extra luminosity throughout the galaxy, it would affect the profile across the luminosity profile across the galaxy versus a non-star-forming galaxy, or one that's quiet.
Yeah, actually that's a good point. I did not consider that, but again, that comes into having more data to observe. So I had a small range of galaxies which I could observe, but if I had a larger set, I could probably draw some sort of conclusion or correlation from that. That's something to consider, I guess. Thank you.
All right, one last question before we stop. Oops.
Thanks for that presentation. Just regarding your little dilemma of sorting out the difference between the ESO and the E9, perhaps with the gear that you've got in the future, you might want to consider doing graduated exposures to overcome the fact that the long exposures are going to basically obliterate a lot of information. I've seen this technique used by the late Alex Vassiliev years ago, and it's really intriguing what can be resolved in the centre of those galaxies and shorter exposures. And of course, it would be nice to get a night without the moon around to get photos. So I just wonder if you want to consider that in the future, that you can actually, you'll reveal a lot more information than what you're going to get from just a standard one-size-fits-all exposure perhaps.
All right, thank you so much.
Great. Thanks to all the speakers that presented this morning. It's now morning tea, and we'll start back in here again with the next session at 11 o'clock. Thanks, everyone.
Thank you.